To all those that have joined already, we still will wait a few minutes before starting officially. Hello, everyone. Again, we'll wait roughly 2 minutes, and then we'll start the webinar today. Hello, of course, to everyone who already joined. Okay, then I would suggest we don't wait too long. So first off, again, welcome to everyone who's joining today's iteration of the FHI-aims webinar series. Again, thank you everyone who's here. Also, thank you one of our speakers, Ray Miyazaki, who's already here and who will also be introduced in a second. So today, the topic of the webinar is heterogeneous catalysis, and in specifically from model to mechanism in heterogeneous catalysis. And we'll have 2 talks today. So I have the pleasure of also giving the first introductory talk, and I will really focus on the FHI-aims software package to give all of you who might be either new users or who have not heard of FHI-aims before the opportunity to find out what FHI-aims is, its design choices, the kind of applications you can work with FHI-aims, and so on. That will be the first talk of today. And then afterwards, we have Ray Miyazaki, who is currently assistant professor at the Institute of Catalysis at the Hokkaido University in Japan. He was also a 2-year postdoc before at the FHI Institute here in Berlin. But he will also give a more personal introduction during his talk. So his talk will be on density functional theory approaches for modeling heterogeneous catalysis. And we don't have just this one day planned for this webinar, but we also have a day 2. And here I really want to point out every one of you is welcome to join. So we will have a hands-on and discussion session in the morning Europe time, so that's 9 a.m. CEST, as well as one later on at 3:30 p.m. CEST Europe time. So if you have not signed up yet for the tutorials, you can still do so. Otherwise, if you have signed up and registered, you should have already gotten an invitation link to join the tutorial session with some more details on what you have to do to actually log onto the resources and so on. So, but as I mentioned, you still have time to register. So if you want to do so, feel free to do during this webinar after. And you should still get an invitation then. We have also set up a Slack channel for general questions concerning the FHI-aims webinar. So this invitation you also get when registering for the tutorials, where you can ask questions during the webinar and tutorials for us to answer. And I also want to I also want to point out that we have a YouTube channel. So if you go to YouTube and type in MS1PEV, you will also find that we produce smaller YouTube videos. In this case, we also have the basics of FHI-aims tutorial, which gives you a first overview of the input and output structure of the code. But more on FHI-aims in a second. So the topic of the tutorial for tomorrow will be on how to simulate SLES systems for heterogeneous catalysis with FHI-aims. So this is really one of the examples that Ray Miyazaki will talk about later on. So here you can see on the right a cobalt nanoparticle on top of an amorphous silica surface. So we'll find out how to model these kinds of systems with FHI-aims. Okay, so then I briefly change my slides here. And then we are ready to start the first talk, which again, I have the pleasure of giving you first talk. And it will be a general introduction to the FHI-aims software package. So to give a brief introduction of myself, so I'm Konstantin Leon. I currently work as a software scientist and also industry relations officer at MS1PEV, which stands for Molecular Simulations from First Principles EV. And you will find out also in a bit what this nonprofit association in Berlin is actually doing. But to start, we of course want to talk about FHI-aims as a code. And I want to point out right away that FHI-aims is not the result of work in one research group or by just a few individuals. It's really a collection of people with contributions of over 150 people nowadays from all over the world, from Berlin, Duke, UNC, so the US, China and Beijing, Helsinki, Cardiff, Dalhousie, Warwick, and so on. So it's really a collection of people all over the world. But FHI-aims as a code has some what we call the aims coordinators. So these are Volker Blum, Sebastian Kockott, Mariana Rossi, and Matthias Scheffler, who are, some of these are also Volker Blum and Matthias Scheffler, also here as panelists today. So I want to thank them, of course, for taking the time. And I want to point out that FHI-aims as a code has really had a long history of code development. So nowadays it's more than 20 years of development. And these 150 people really has to be pointed out in more detail. So this is from our website at FHI-aims.org, where you can find the full collection of people that contributed to the code base. And this is still, we are pretty sure, not complete, but we just want to take this time to really thank those people for doing the actual work that we'll showcase here today. And to again summarize a bit what the FHI-aims code is, it's really community-based. That means it's really an open development platform. So if you're a research group, whether in industry or in academia, and you're interested in developing new research, new ideas, and you want to implement those, FHI-aims is really in that sense open for you to do your independent developments. So, and these new physics and developments are constantly being added really by scientific groups around the world without really any significant oversight by anyone. So if you are really interested in just adding science and contributing to the code, you're free to do so. Now, I already talked a bit about MS1P. So MS1P, Molecular Simulations from First Principles, is a German nonprofit association. And the main mission of MS1P is really to promote basic science. And what we do in the context of FHI-aims is we try to help with code stability and integration. So if there are issues with integrating new features into the code or just stabilizing the code in general, we'll try to help out. We are also here for community support. So we manage, for example, the community channels for FHI-aims, which is the Slack channel as well as the development GitLab channels. And we're working on documentation, webinars such as this one, online tutorials and conferences and so on, as well as, for example, here, collaboration with industry partners on specific research questions. So we're really trying to help the community as a whole that surrounds FHI-aims. And MS1P and its structure has an executive board. So that's Professor Matthias Scheffler, who's here, who's the chair of the board, as well as Volker Blum and Mariana Rossi. So that's really a brief overview of what FHI-aims and MS1P are, in case you were interested maybe what the distinction is between the two. Then let's go to the actual design principles behind what makes FHI-aims what it is. So from the onset, there was a vision that FHI-aims should be able to perform quantum mechanics-based simulations of real molecules and materials and their properties without a priori precision and accuracy limitations. And that was really something that had to be, was decided from the onset. So there were a few design choices that were needed or decided on to fulfill this vision. So one, FHI-aims should be an all-electron code. It should be able to handle non-periodic and periodic systems on equal footing. So whether you have periodic boundary conditions or not. It should scale to extremely large systems, so that can mean thousands of atoms, or as you will see later on, even 10,000s of atoms, without limitations. It should scale both on laptops as well as massively parallel HPC architectures. And in the end, the main focus in the beginning was on density functional theory, but also correlated methods. So whether you're interested maybe in RPA, GW, coupled cluster, and so on, this is also supported within the code. And the key design choice behind FHI-aims is really what kind of basis set you choose. And in this case, it's the numeric atom-centered basis functions, because they allow for an accurate representation of the orbitals as well as the densities. So let's dive right in. Let's say talk a bit more about these atom-centered orbitals. So as you might know, if you're familiar with DFT or quantum mechanics-based codes in general, you typically start from a basis set expansion, and then you have here an expansion in terms of basis functions phi I. And these phi I, you are free to choose what kind of basis functions you want to use. As mentioned, FHI-aims decided on numeric atom-centered orbitals, which are shown here on the right side. And you have a part with Ui over R, which is the radial part, as well as the spherical harmonic part. And the reason this was chosen, and you can see the structure here of the radial function down below, as that this is not an analytical function, but rather a numerically tabulated one. So you are quite flexible in what kind of choice of basis functions you want to have. And this also means that the very strong variations near the nuclei can be quite well described already with these kinds of radial functions. And we have the possibility to define, for example, here a cutoff potential to really set an exact zero at some type of radius. And what this gives you, let's say in a nutshell, is one, you have this extremely flexible shape. All these atom-centered or radial functions are tabulated on a dense logarithmic grid. So you really have the flexibility there. You naturally have an all-electron description. So within FHI-aims, there's no, let's say, a distinction between what are core electrons and valence electrons directly. They're all included naturally. And of course, because these are atom-centered, so they're really localized, you can have O of n computational scaling for the most expensive steps. And that's, of course, really important for us to gain good scalability to larger system size. And in the end, because you also have, for example, here this cutoff potential, you actually need a rather compact basis set if you want to get more or less converged results with respect to here total energies in most systems. Then the important thing is you are quite flexible, but you still have to decide on what kind of basis functions you want to use for all the elements. And so for this, within FHI-aims, you already have a basis set library available for the elements 1 to 102, which differ in whether you want fast qualitative results to really milli-electron converged results with respect to DFT calculations and total energy. We also have basis sets that go beyond just simple DFT. So for example, if you're interested in GW calculations and so on, we also have specialized basis sets for those kinds of calculations. So, and we hope with this, or we think that this really makes it also easier for new users to start right away, because they don't have to handle all of the specific basis set setup, but you always have the flexibility to change things yourself. So that's really one of the main key parts of the code. So you can just change stuff to your liking, of course. So it is high precision of FHI-aims for DFT calculations has already been also shown in literature. So this is, some of you might know this is the delta test, which was published in 2016. And the main part here that was checked was the energy versus volume curves for 71 elemental solids. In total, 15 codes were compared between all electron and pseudopotential codes. And here actually the FHI-aims results, which you see in the second row, were not obtained by us, but rather by Marcin Dulak at the DTU in Copenhagen. But what you can nicely see is that FHI-aims is really extremely accurate and on par with all the other all-electron code-based implementations here. So this is really, of course, one of the main pillars we want to focus on. So we want to be precise, we want to be accurate, but we also want to be efficient. So this is here the reference again for the delta test. We also have other references you can take a look at. For example, here, this is the paper on the GPU acceleration of FHI-aims. So we have partial GPU acceleration to also allow these efficient computations on newer architectures. We have, for example, also a band structure benchmark with spin-orbit coupling, if this is what you're interested in. As well as, for example, here, a relatively recent roadmap article that really describes what FHI-aims is doing to go towards the exascale. So then I wanted to point out one specific, really more or less recent advancement in our eyes, which is hybrid density functional theory. So for a while, FHI-aims has been able to do GGA, LDA-based simulations for for several thousands of atoms, which with more or less optimal scaling. But the same for hybrid DFT required a lot of work. And here I want to point out this is really work over more than a decade. So this really has to be, let's say, stressed that this is a lot of work by all the people involved. But we're really happy that this is in the code now. So what you see here are some benchmarks for gallium arsenide supercells with the hybrid function HC06. And what you see here is the strong scaling. So ideally you have O of n strong scaling. And as you can see, the new implementation, and you will see also in a second actual systems, which may be more of interest than just gallium arsenide, we were able to, or the researchers, including Sebastian Kokot and others, as you will see, were able to reduce the time to solution by up to 2 orders of magnitude, as well as achieve almost ideal scaling even over thousands of cores. So as you can see, the end of the x-axis here is nearly 10,000 cores that were run on an MPCDF. So that's the Max Planck Data Facility CPU cores. So that's really, I think, amazing achievement. And the same is also in terms of scaling with respect to the number of atoms. So not just with the number of MPIs tasked, but also with the number of atoms, we almost achieve ideal O of n scaling. And why this is now, of course, very exciting is that you can go to much larger systems than what probably a lot have thought is possible with hybrid DFT. So in this benchmark here and in this paper, these were the largest systems that were tested. So you can really see it's hybrid perovskites, it's paracetamol supercell, and then you see on the right side, both of these plots are larger ice supercells. So the largest cell that was simulated is an ice supercell with over 30,000 atoms. So that's almost 250,000 basis functions, which was able to be run on just 60 CPU nodes. So I think that's already quite amazing. And you can see that at this kind of system size, the bottleneck is really what we call here ELPA. So that's the eigenvalue solution. So ELPA here is an external library to solve the eigenvalue problem, something we'll see also later on when I will talk a bit more about the FHI-aims ecosystem. So what this now enables, which I think is very exciting, is really large-scale simulations. And for that, we need a host of features, of course, which are implemented in conjunction with these hybrid density functionals. And this is an excerpt of the roadmap, which is on advancement of the FHI-aims software package, which is, fingers crossed, soon to be published as a preprint, maybe already before Easter. So yeah, maybe you're lucky enough, and this is an Easter present for you to read. But one part is these hybrid functionals, which have support for several things, such as forces, stresses, dispersion corrections at many different levels, whether it's a D3 correction, many-body dispersion, or XDM, and all kinds of output functionality as well. And what we've already seen in recent times, so these are two recent papers, is that this now really allows other researchers to also create extremely high-quality data sets. So data sets currently, when used for machine learning, foundation models, and so on, are mostly based on GGA or GGA plus U level calculations. But we think now that with FHI-aims, this really allows also to do extremely high-quality, hybrid density functional quality data sets. So for example, here, both these papers have used PB0 plus MBD to calculate the total energies as well as other properties. So MBD here is the many-body dispersion correction. And the first paper that we show here actually has 33.5 million FHI-aims DFT calculations in the database. And they trained this on molecules ranging with elements all over the periodic table. So the hope, and we have to see if that's actually achievable, and other researchers would try those, of course, to have a foundation model based on hybrid level DFT. So we'll see what comes out of this data set, but I think this is quite exciting development already. So this is work here from the Google DeepMind team, also in the group of Klaus-Robert Müller. And the second paper here is also from Klaus-Robert Müller, as well as Alexander Tchachenko, where they also trained or created a data set with PB0 plus MBD for biomolecules, and then used this to train already a neural network force field. So I think that's already quite exciting development in this direction. So that's FHI-aims and some more focus on the hybrid functionals, but FHI-aims as a whole is, of course, a large ecosystem. So you have the main FHI-aims package, which really does the electronic structure-based part, but FHI-aims is really based on several external libraries which are open source and which I think is critical for any kind of electronic structure code. And that includes, for one, ELSI. So ELSI is the electronic structure interface library, which gives other codes and which is also used by several codes to gain access to different eigenvalue solvers and just general things that are needed for electronic structure calculations. We also have support for several exchange correlation functionals via libxc, as well as the dispersion corrections via libmbd. And then even going beyond, in this case here, we have an interface to CC4S to do also coupled cluster calculations. And that's the basis of the driver, but FHI-aims as general also has support for external workflow drivers. So that's here, for example, IPy, the ASE Python package, Python, FHI-vibes, and so on, and many more, as well as a graphical interface, which we call GIMPs. And GIMPs is something that if you participate in the tutorial tomorrow, is something you will also then see there. And I just wanted to briefly mention FHI-aims can also be used as a library. So we have, for example, the atomic simulation interface is directly supported by FHI-aims. So if you want to extract a Hamiltonian, for example, to train on the Hamiltonian and stuff, this is also possible. We have additional Eclipse Python package, which is a collection of command line tools to hopefully ease the burden of creating input files and analyzing results. Support for several workflow managers, which some of you might know quite well, like Automate2, AIDA, Task Blaster, and so on. And then lastly, something we've worked on relatively recently is PyFHI-aims. So that's really a dedicated FHI-aims I/O library, which we hope will make development much easier for the future, also for new developers. Okay, so that's the ecosystem. Now, maybe, or hopefully, I gave a good introduction to the code, and maybe you're interested in getting some more information, maybe trying out the code and so on. And there I would really suggest to go to our website. So that's FHI-aims.org, so FHI-aims.org. And here you have the option 1 to click on the Get the Code page. This will give you all the details if you're interested, how do we get the code? Keep in mind for academic groups, it's only for a voluntary license fee. So if you're just interested in contributing and so on, you can freely do so. Just go to the website to see. And then one other thing I want to point out, which I think is very important for new users, but in general also just to showcase research, are the online tutorials which we have. A lot of them have been contributed by external people. So again, I want to point out the big work that has come here from the community. And this tutorials page is really already quite extensive and it just keeps on growing. And we're really happy that it does. And it goes from all kinds of topics, from fundamentals of FHI-aims, just how do you run the code, to how do you use different machine learning algorithms with FHI-aims, beyond DFT, molecular dynamics, complex workflow, spectroscopy, and so on and so forth. So this, I think, is a really good first step if you just also want to see maybe FHI-aims in action. And one of these tutorials, we will do tomorrow, as I already mentioned. And if you're interested, please feel free to join there. And then the last thing I want to point out is, again, our YouTube channel, because we try to also give some more visibility, maybe in a visual sense. So we created some smaller YouTube videos on the basics, on different tutorials that we had in the past, like the fusion barriers, how to calculate thermal transport, how to do these kinds of dispersion-corrected hybrid DFT calculations. So if you're interested, please also go to the YouTube channel, check them out, give us feedback, of course, if you would like to see something specific. And then with this, I'm already at the end of this short introduction. And I want to just summarize briefly. So FHI-aims is really an electronic structure code based on numeric atom-centered orbitals. And with this, I think we really enable very versatile system calculations, meaning you can do molecules, clusters, surfaces, as you will see in a second, slab systems, solids, liquids, all on the same footing. I think we've shown that we can be very precise and accurate. We can do large-scale hybrid DFT, including dispersion corrections, but also go to many-body methods. And we are scalable even on small machines like laptops, but up to 10,000, of course, on HPC systems. So with this is it for the introduction. I want to thank you all again. And yeah, the session is open for questions from your side now. Thank you. And yeah, in case you're not aware how to ask questions, so we'll use the Q&A functionality of the webinar. So if you have questions, there's a Q&A button which you can click and then just ask your questions and we'll go through this. Yeah, and the actual Q&A will be led by one of my colleagues, which is Andrei Sobolev, and I think he can just introduce himself now. Thank you.
Yes, so if you have any questions, please feel free to ask.
Of course, if in case you don't want to ask the questions now, you can also do so later by email or by the website where you also have our contact information, of course.
Oh, okay. There is a question by Ahmed Mahmouda. The question is how well the code scales on multiple GPUs for the calculations involving hybrid functionals.
Yeah, that's a good question. So it was mostly focused on GGA functionals at the time. This is a currently active work, so the GPU implementation is being worked on, and is one of the topics that we want to address also for the future. So we hope that these scaling improvements can also be there for the hybrid functions. So at the moment, I think the speed up is not drastically there for the hybrid functionals, mostly because we would have to optimize the exact exchange part to also scale well on the GPUs. So I would say this is active work. if you're really interested in using GPUs for hybrids, I don't know the exact benchmarks at the moment, but yeah, I would just say it's active work. I don't know exactly the performance there.
Thank you. There is one more question by Ashok Kumar. Can FHI-aims be integrated with crystal structure prediction methods?
Yes, thank you, Ashok. So yes, this was actually done or is being done. So one of the industry partners we have is Avant-Garde Materials Simulation, who are one of the, let's say, main providers for crystal structure prediction in industry, and they really have shown that PBE0 calculations for FHI-aims, including dispersion corrections, are really are one of the ways to go to really get accurate crystal structure predictions. And I think if you maybe know also of the blind tests, the recent blind test that was done also demonstrated that, let's say, what you call the best performing team was actually the group from Markus Neumann working with FHI-aims. So I would say absolutely it can be integrated with crystal structure prediction methods. Specifically, the hybrid functional implementation is there key.
Thanks a lot. I don't see any questions open in the queue. Oh, yeah, there is one question from the anonymous attendee. Technical question. You said the radial basis functions are not analytical but tabulated. I thought they were hydrogenic functions generated by solving the H-Adam-Schrödinger equation with some modifications, additional potentials. Is this considered not analytical, or are the basis functions generated differently?
Yeah, that's a good question. So maybe, I don't know if I can refer here to Volker, who was really the main developer and who knows best about these basis functions. So maybe he can give a better answer than me there.
Yes, yeah. So you can toggle this behavior. So if you want the hydrogen-like functions with the cutoff potential that cuts off zeros, trailing zeros smoothly at a certain radius, that's best for performance, and that is done numerically. But you can toggle a switch, and then you can get analytical hydrogen-like functions also. That's documented in the manual, except then, of course, they're extended as analytical functions would be with an exponential tail, but they work.
Thank you, Volker. I hope that answers the question. If you have, of course, additional clarifying questions, feel free to ask again.
Actually, I'm not sure if this was really the question. I mean, I understood the question if it is only hydrogen type of functions. In principle, actually, it's not only. I mean, you can do hydrogen functions, but what we typically do, we solve really the numerical Schrödinger equation for a free atom, right, with a cutoff potential, so that the wave functions do not range too long. But it's actually really having all the information of a free atom. And that's why they are so efficient.
Yes, yes. For the minimal basis and for the atomic-like functions, that's of course true. And there are more basis function types. I guess this question goes on. There's a question what you call analytical. For example, Gaussian functions, of course, can be tabulated on a radial grid. And we do. And Slater-type orbitals can do the same thing.
Thanks a lot. There is one more question from Dr. Tagema. Is it possible to extract the radial densities and/or radial energies of systems from the output files for calculations performed using FHI-aims with DFT methods?
So I'm guessing here you're interested in the actual basis function form and on what you get out and so on. I think, yes, you can extract those from within the code. I don't know what the specific keywords which you can use, but I'm sure there are some to actually output the radial functions and what we have as basis functions. But I don't know, Volker, if you have on the top of your head what's mentioned in the manual there, what kind of keywords you can use here.
So the question is, what is a radial density? I would have to ask more specifically, what is a radial density? So of course you can actually print the decomposition of the full density of an extended system into atom-centered multipoles, and then you get atom-centered multipole densities. Radial energies, I'm not 100% sure how to interpret that without a better definition, but maybe I'm just flow, which could be. But all these things can be printed if we know about them and given time, right? Often we don't know the use case, and once we know, that's actually for the other question. That's a very interesting question. I don't know if we can briefly jump over there, right? Because that asks about heterostructures, right? And as you probably saw in Konstantin's talk, we have FHI-aims, which includes a simple structure builder. I don't think it has a heterostructure building tool yet as a matter of being integrated there, but I think the underlying ASE has something like this. And so I don't think it should be too hard to put a heterostructure builder into FHI-aims necessarily. It's just something we need to know, but this is still something needed. And so it's useful to make those cases with us, and it can be done. That's actually, that second question is a very good point.
Yeah, I agree. So, I mean, the question was essentially, Leah wants to make heterostructures, but most of the programs to do so are not free. As Volker mentioned, we have FHI-aims, and tomorrow, if you're interested in the tutorial, we'll also go briefly through the FHI-aims structure builder. So, what kind of structures you can build. The main thing is, as Volker already mentioned, we don't have, let's say, single button clicks to create these heterostructures. If that's really of interest, and that's something that's really good for the community, I think this can be extended. So the ASE library, as well as PipeEngine, I'm sure has utility functions to create such heterostructures. And this, of course, you can also just use. So if you are familiar with Python, so more like command line interface stuff, then you can create the heterostructures also there. This sounds more like you want to use a GUI, so really a visualization type thing. So that's possible in FHI-aims. You would have to do more manual work. But if you're just interested in how to create slabs, for example, so starting points for your heterostructures, this is also shown tomorrow in the tutorial. So I hope that answers the question more or less completely.
Okay. I don't see any questions in the Q&A section. I also don't see any questions in the YouTube channel.
Okay. Great. Yeah, well, then I think we can go to the next talk here. Of course, if you still have questions, you can still post them in the chat, and we can also just answer via the Q&A functionality. So we'll just type in the answers. So yeah, again, it was my pleasure to give this first introductory talk. And now we really go to the scientific part of this webinar, which is on heterogeneous catalysis. And here we'll hand over to Ray Miyazaki. And he will also give a brief introduction again to who he is and what kind of work he's doing. So Ray, I will stop sharing, and then you can start sharing your slides.
Yes. Yes, I hope it is fine now.
Yes, we see it now. Yeah.
Can we start my talk now?
Yes, you are ready. So I can see
Okay.
everything should work.
Yeah. So hello everyone, I'm Ray Miyazaki from the Institute for Catalysis, Hokkaido University, Japan. So first, it is my great honor to join this very nice FHI-aims tutorial. So then I'd like to thank for Konstantin and the other people of the MS1P and the FHI. So today, I'd like to talk about the density functional theory approaches for modeling heterogeneous catalysis. So before entering my talk, I would like to briefly introduce myself. So my name is Ray Miyazaki. So currently, I'm an assistant professor at the Institute for Catalysis, Hokkaido University. So actually, I got a PhD in the same laboratory with Professor Junya Hasegawa. So, and then I did a 1-year postdoc, and then from 2021, I moved to the Fritz Haber Institute of the Max Planck Society as a postdoc. And at that time, I worked with Dr. Lucas Fopper and Professor Matthias Schäffler. And then from 2023, I moved back to Japan and then become an assistant professor. So now I belong to the Hasegawa group. So now we have the 10 members. Actually, it is relatively small group, but I believe that we are a very active group. So, and this is a brief introduction of our institute. So here, this is a map of the Japan, and here's the Tokyo and the Kyoto in the main island. But our institute located in here, Sapporo City, so located in the northern island of the Japan. So the Institute for Catalysis has the 9 research divisions with 25 faculties. And actually, our institute is relatively small, but they have the long history. Actually, our institute was established in 1943, and this is the oldest research institute named after the Catalyst. And also, there's a historical long friendship with our institute and the Fritz Haber Institute. So, and because our institute located in the northern part, in the winter, we have a lot of snows. Actually, I took those photos by myself in our university in midwinter. And nowadays, of course, the amount of the snow at the road is decreased and decreased, but still we are in winter. But soon, probably several weeks after, we will have a nice spring season. Then I say Hokkaido is a very nice place and our institute is very nice. So, and this is a very brief introduction of myself and the institute. So let me start the scientific part. So first, I would like to talk about my scientific interest. So this is a very typical equation of the chemical reaction. Here, A plus B generates a C molecule. And if you add the catalysis and with temperature and pressure, we can control the, how to say, the product of the C or ratio of the C. And this reaction connected by this arrow. But point is, in the textbook, there's a very limited description about the mechanism behind of this arrow. So then my interest is what is happening behind these chemical reactions during this arrow. So then my research purpose is proposing the reaction mechanisms and the design criteria for new catalysts by theoretical calculation and recently AI. So for example, by using ab initio calculations with like a DFT, we can get this kind of reaction pathways of the catalytic reactions. And then from this, we can extract some kind of catalytic mechanisms. Or we can use experimental and or theoretical data, and then we can combine those data by using artificial intelligence, and then we can get some kind of descriptive parameters that correlate with the target catalytic performance. And then by using those approaches, we can get a design criteria for new and high performance catalyst. And this is my, how to say, the main research topics recent days. And so, and the target is heterogeneous catalyst. And most of you already know the heterogeneous catalyst is very essential and important technology or materials for the modern society. For example, this can generate the useful chemical compound from raw materials. And then we would like to develop a new and high performance catalyst. But the problem is the heterogeneous catalyst itself has very highly complicated structure. And that means there's a lot of factors that affect the catalytic activity. Here, this is a very typical picture of the heterogeneous catalyst. Here is a metal nanoparticle supported on the support material. And for example, here, metal, of course, metal surface is the active site, but also interfacial site between the metal and the support material is a very important active site also. And this metal nanoparticle itself also has a very complicated structure, like several facets and several active sites. Then, due to this complexity, what kind of reactions takes place where in the catalyst is a very big question for us. And of course, the mechanism of catalytic reaction that proceed in the atomic scale is hard to be elucidated only by experimental approaches. Then, electronic structure calculations. So because by using these electronic structure calculations, we can get atomic scale reaction pathways and effect of electric state of the catalyst to the mechanism. Then it is very nice approaches, but problem is due to this complexity, it is very hard to explicitly include all of the structures and factors of the catalyst to the atomistic model with ab initio calculations. Then we need to extract the factors that essentially contribute to the catalysis that enable us to the elucidating the underlying mechanism and principles of the catalysis. And also, I was to stress that we need a collaboration with the experimental groups because by using both sides of the narratives from theory and experiment, we can propose the design criteria for the new catalyst from both sides. So this is a very general introduction of the heterogeneous catalysis with eclectic structure calculation. So today, I would like to focus on the one application of my DFT calculations for this CO2 hydrogenation by cobalt catalyst. And most of the results are published in those two papers. So, and in this project, I focused on this cobalt catalyst. Here, cobalt nanoparticle is supported on the modified amorphous silica support. And the important point is some kind of these additive metals are incorporated in the silica support. And in this kind of catalyst, not only this metal nanoparticle, but also the support material and the interaction with them are very important for the catalytic performance. Then the difference of the support material is very important for catalytic activity. But the design criteria for the optimal support materials are not fully established yet. Then in this study, we particularly focus on the role of the modified silica support for the CO2 hydrogenation by using this catalyst. And this catalytic system is quite unique because our collaborators, mimic the hydrothermal vent environment by using this catalytic system. Hydrothermal vent is the fissure on the seafloor, and then discharging some hot water from the seafloor. And this related to some kind of origin of rise. And then our collaborators investigated how first organic molecules are generated at the hydrothermal vent by using this catalytic system. And this is computational details for my research. And of course, all of the calculation performed with the FHI-aims. And even though, the version of the FHI-aims is a little bit older, but it was very nice. And I performed all of the calculation in DFT level and with RPB functional. And because the ground state of the cobalt is a ferromagnetic state, then I adapted the spin collinear calculation for simulation. And for geometry optimization, I adapted the right basis set. Then by using the optimized structure, I performed the single point calculation with tight basis set to get a reliable or more accurate electronic structure and the analysis. So then we would like to perform some kind of DFT calculation for this catalytic system, but then we need to build the theoretical models of the target system to perform this. But there are difficulties to achieve this. For example, this is a target catalytic system. For example, for this metal cobalt nanoparticle, the experimental particle size of the cobalt is about 8 nanometer. That means it is super large for DFT calculations. Then we cannot be handled directly with DFT this size of the metal nanoparticle. And for support material, the support material has the amorphous structure. Then one question is how to model this kind of non-crystalline amorphous surface with DFT. And the final one is there are incorporated metals into the silica, but how to incorporate those additive metals structures? What is the structure or what is the electronic structure of them? Then, and also, since the experimental information is limited, detailed structure like shape or morphology is unknown for this kind of heterogeneous catalyst. Then, explicit atomistic modeling with DFT is rather challenging. Then, practically, we need to focus on the physical-chemical properties of the catalyst that would correlate with the performance. For example, first, this cobalt nanoparticle part, again, this is a super large for DFT, then I adapted this cobalt-20 cluster model. And actually, cobalt-20 cluster here is about 0.5 nanometer. That means this is super small than the actual particle size in experiment. But this is a very, how to say, practical size for simulation. But fortunately, there's one previous study. Based on that study, from around the cobalt-55 size, the adsorption energy of the small molecules is almost constant against the size of the cobalt cluster. That means this cobalt-55 is a lower limit for simulating the cobalt nanoparticle with small molecule. Then that the result with cobalt-20 model can be compared with those of the cobalt-55. Then if result is qualitative or quantitatively similar or same, that means the cobalt-20 cluster model is one of the, how to say, the reliable model for the simulation. And for silica, this is also fortunately, the amorphous silica surface model was already built by using MD, molecular dynamics, and the DFT calculations by Thomas Bibbs. And then in this study, they performed the molecular dynamics simulation with high temperature, and then making non-crystalline structure, and then gradually cooling down the simulation, and then finally gets this kind of amorphous silica structure. Then I picked up this model from this literature and then performed the geometry optimization with our computational setting, that is FHI-aims with RPB function. So then now we have the two models, that is the silica surface and the cobalt cluster. But next question is how to put this cobalt-20 cluster onto the amorphous silica surface graph. Because as I mentioned, this is the amorphous surface, then that means there's no symmetry of the surface. Then we can freely put the cobalt cluster onto it. Then based on this previous study, this kind of metal nanoparticle contact with the silica by removing the hydrogen from OH group. That means by contacting the metal nanoparticle, this metal nanoparticle directly bonded with the silica via oxygen atom. Then, as you can see here, I counted up the OH group on the surface of this model, and there's a 32 OH groups. Then I put the cobalt-20 cluster model right above each OH group, and then removing the hydrogen atom that directly contact with the cobalt nanoparticle. And then I performed the geometry optimization on each point and comparing the relative stability of them. And this is the result. And I actually calculated the formation energy of this cobalt-20 with silica slab. And this is just means the negative energy with this energy, this equation means the stable structure. Then here, y-axis represents this formation energy, and the x-axis represents the index of the structure. Then I perform the geometry optimization of each point, and then I finally got the most stable one, this one, number 23. And this structure shows the minus 2.24 electron volts for formation energy. And then that means this is very enough stable for this contacting the cobalt cluster and the silica slab. And this is the obtained most stable one. This is the top view, and this is the side view. And here, cobalt nanoparticle, cobalt cluster model is contacted with this silica with 5 OH group without hydrogen. And the next question is, okay, now we can get this kind of theoretical model for cobalt catalyst, and then what we can do. So first, we can, of course, investigate the electronic structure. Here, I investigate the atomic charge of each cobalt atom. And then by using high-field charge analysis, we can get this atomic charge. And then in FHI-aims, you can use this kind of keyword in control.env file. And here I show the result of the Hirschfeld charge analysis, and then I picked up the top 3 negatively charged cobalt atoms and the top 3 positively charged cobalt atoms here. And this is the blue one is a negative one, and the green one is a positive one. And as you can see here, most of the positively charged cobalt atoms are located at the interfacial site with the silica, but the negatively or neutrally charged cobalt is located at the top layer of the cobalt cluster. Then that means the the cobalt at the interfacial site has the positive charge or cationic cobalt due to the interaction with the silica sample. Then we can get such kind of electron structure information from those kind of calculation. And then next, of course, because we are interested in the catalysis, that is CO2 hydrogenation, then we are interested in the interaction with molecules and the catalyst. And here I investigated the interaction with CO2 and this cobalt cluster model. And I calculated the adsorption energy of the CO2 here. This is the energy of the total model, and the isolated model energy of the isolated model is subtracted. And here, because as you can see here, there's a lot of adsorption sites of the cobalt cluster. Then the question is how to put or where should we put the CO2 molecule on this model? And then I picked up the most negatively charged site and most positively charged site of the cobalt cluster. Because as I showed before, we know there's some different charge balance inside of the cobalt cluster. Then I'm interested in this difference. So here, this is a CO2 adsorption structure as the most negatively charged, or that means metallic cobalt site. And the actually calculated adsorption energy is minus 0.5 electron volt. But for the cationic site at the interfacial site, adsorption energy calculated to be the minus 0.27 electron volt. That means the CO2 prefer to be adsorbed at the metallic cobalt site here. And then this interfacial site is not the most stable or preferable CO2 adsorption site. And as I mentioned, cobalt-20 cluster is too small for actual, compared with the actual cobalt cluster. Then we need to assessment of the reliability of this cobalt-20 cluster. Then, as I mentioned before, this can be done with cobalt-55 based on the previous study. And I also constructed this cobalt-55 SiO2 model with this cobalt-55 cluster. And I put the CO2 at the most negative side and the most positive side again for cobalt-55. And as you can see here, the CO2 adsorption energy for metallic cobalt site is more stable than interfacial site. That means this trend is same with the cobalt-20 cluster model. Then, the adsorption trend of CO2 is qualitatively, not quantitatively, but qualitatively represented by cobalt-20 cluster model. Then, even though cobalt-20 cluster model is smaller than the experimental particle size, but that model has some kind of reliability for the simulation of the small molecular interaction with cobalt nanoparticle, with DFT. So, and then now we can get some theoretical model of cobalt cluster onto the amorphous silica. And then the remaining question is how to incorporate the additive metal to represent the difference of the support material. But the problem is we only know the experimental metal-silicon ratio. That means the actual structures are unknown. Then we need to focus on the specific point of the catalyst. Now we are interested in the interaction between cobalt and additive metals at the interfaces. Then I decided to focus on the additive metals in the stable oxidation state at the interfacial site. So this is what I mean. So actually I incorporated those additive metals with keeping the stable oxygen state of each metal. For example, here, this original silicon and the titanium or zirconium generally prefer to be the 4+ oxidation state. then I simply replace the silicon atom by titanium or zirconium. Then, this additive metal side interact with the 4 oxygen atom. That means this additive metal has the formally 4+ oxidation state. But for aluminum prefer to be a 3+ state. Then once I replace the silicon atom simply by aluminum, the charge balance is unstable. Then we need to keep a system to be neutral. Then we need to put the 1 proton as the oxygen atom surrounding the aluminum site. And then in this model, I put the aluminum and also proton as the interface site. And for finally, calcium and magnesium, those metals prefer to be 2+ state. Then I put those metals at the bridge site between 2 OH groups by removing the 2 hydrogen atom like this. And then this metal interact with the 2 oxygen. That means this metal to be formally 2+ oxidation state. Then of course, there's a lot of possibility for the actual or operanto structure of the additive metals into the silica support, but I put the one assumption, probably those metals prefer to be a stable oxidation state itself. Then remaining question is, where should we incorporate the additive metals onto the silica support? And again, this cobalt-20 cluster is directly interact with the 4 SiO4 units. Then at the interface side, then I simply replace those silicon atoms by titanium and zirconium, and then compare the stability. Here, this is a result. And actually, I replaced the A, B, C, D silicon by titanium and zirconium, and then calculated the relative stability. And then based on this calculation, replacing this D site is the most stable one for titanium and zirconium. And a similar strategy adapted for aluminum and calcium and magnesium. And then we can decide where should we put these additive metals onto the silica. And yes, and by using those obtained cobalt-20 SiO2 model, we can investigate the difference or effect of the difference of the support material. For example, this is a result of the CO2 adsorption at the interface side of each model, titanium, zirconium, aluminum, or something. And then here is the calculated adsorption energy. And as you can see here, the obtained adsorption energy of the CO2 at the interface site is actually quite different depending on the additive metal. That means even though I just put the one additive metal, this is quite far from the experimental silicon metal ratio, but this very simplistic model can represent the difference of the support material for CO2 adsorption. And we can also extend to the reaction mechanism. And this is a brief reaction mechanism of the CO2 hydrogenation. This is a very brief one, but as you can see here, the CO2 hydrogenation is very complicated. But there's 3 main reaction pathway was proposed by this paper. The COH generation pathway, CO generation pathway, formate generation pathway. These are those 3 intermediates recognized as the very important initial 3 reaction intermediate for CO2 hydrogenation. And for methanol formation, this methoxy intermediate recognized as the final intermediate. And then I picked up those 4 key intermediates, and then I investigated the adsorption energy or relative stability of those key intermediate onto each cobalt model. And like this, I put the formate, COH, CO, and methoxy at the interface site of each model, and they calculated the relative stability. Here, this is a result with different additive metal. And as you can see here, the relative stability of each intermediate is quite different depending on the type of additive metal. Then that means the preferable reaction pathway of each additive metal would be different. That is very important result. And of course, by using those information, we can further extend to the reaction mechanism investigation. For example, we can calculate the transition state, the connecting the each intermediate, what I showed before. And then finally, we can get energy diagram here. This is a y-axis represents the energy, and the x-axis represents the reaction coordinate. And then we can get the reaction pathways. And by comparing those pathways, we can get main reaction pathway towards the target product. And this kind of calculation can be achieved by using natural elastic band calculations with atomic simulation environment and FHI-aims. And or you can get some more detailed electron structure analysis here, even though this is a different catalytic system, but performed with FHI-aims. For example, this is a charge transfer from support material to the supported gold cluster, and you can get some reason or mechanism for the high activity of the catalyst by using this kind of analysis. And this analysis can be achieved charge density difference analysis by using output cube total density in control.in file of the FHI-aims. And then by using those kind of information, we can get some design criteria for new catalyst. And even though, sorry, actually, those kind of investigation was not performed with the cobalt catalyst, but those calculations actually performed in this paper. Then if you are interested in, please check this paper. And this is actually my approaches for heterogeneous catalysis with DFT. And actually, as you can see here, DFT calculation is very powerful for investigating atomic scale process, that is the atomic chemical reaction that surface is very powerful for DFT. But actual, heterogeneous catalysis is interplay of between the multi-scale processes. For example, transportation of the reactant product gases at the experimental reactor. This is a macro scale, or reconstruction of the catalytic material under the reality experimental condition. This is a meso or micro scale process. Then, it is very difficult explicitly modeling of the full catalytic progression by using DFT calculation. But of course, atomic scale information hard to be obtained from experiment. Then another idea or another application is, of DFT is we can integrate DFT data with experimental data by using AI. But the time is limited, and also, today's main focus is the DFT. And Konstantin mentioned that the upcoming FHI webinars is other speakers will focus on the AI application with FHI-aims. Then I will not detail talk about this, but we can achieve this. And for example, we can get some, we can combining experimental data and the DFT data with AI, and then we can get this kind of descriptive parameters of the target catalytic performance. And also, this AI is obtained by this approach developed in the FHI, and we can get some analytical expression for the target catalytic performance. And this descriptor contains both experimental data and the theoretical data, and we can get some very good starting point for investigating the further catalytic mechanism behind the reaction. And for this, of course, DFT calculation is very useful to extract some information. And also, of course, we can screening the candidate materials with high performance by using more, how to say, the AI model with raw acquisition cost data, and then we can quickly screening the or predict the catalytic performance of the candidate materials, and then propose the new material for experimental group. Sorry, the final part is very quick, but I hope the upcoming FHI webinar will focus on the more detail about the AI approach for the heterogeneous catalysis. But my conclusion is, of course, DFT calculations with FHI-aims are very useful for simulating the heterogeneous catalysis. But unfortunately, heterogeneous catalysts have complicated structures, and thus we need to focus or extract the important part of the catalyst. And as I showed, by using the DFT calculations, we can access the underlying mechanism of the catalyst, and those insights can be combined with AI. And the more detail are summarized in those papers. And finally, I'd like to thank for my collaborators, and the Professor Matthias Schäfer and the Dr. Lukas Foppa at the Fritz Institute and the Nomad Group. And the experimental collaborator is Harun and Kendra at the Max Planck Institute for Core Fusion. And I would also thank for the funding from the Big Max and the FunCat project. And thank you very much for your kind attention.
Thank you, Ray, for your nice talk. Thank you for staying on time. So this was all perfect. So I think we can continue with the Q&A part. So I will hand over again to Andre to handle questions. Feel free again, write in the Q&A chat box. You can also write on YouTube if you're watching there, and we'll see it as well as on Kusha. So I'll hand over here, Andre, please go ahead.
Thank you, Ray, for a very nice presentation. So if you have any questions, please feel free to write. Okay, we'll give some time to type in the questions, or you can raise the hand and we can let you speak if that's more convenient to you. Okay, there is one question from Ashok Kumar. Does FHI-aims support on-the-fly pseudopotential generation for such complex heterogeneous catalysis calculations?
Actually, is it better to answer by myself, or should I ask the Volker? But in my understanding, first of all, FHI-aims do not use the pseudopotential. Probably he would like to talk about the machine learning potential, like implemented in BASP, like. I'm not sure, but in my understanding, there's no implementation, right, Volker?
Yeah, no, so in parts that's because FHI-aims is actually efficient with the all-electron implementation. I think that's a relatively frequent question. So what we're trying to avoid is to actually have to parameterize pseudopotentials, because we can do the calculations with the method that does not need to change the underlying potential with various problems that could arise. Now, that being said, so pseudopotentials come up as a frequently asked question. And so it is on the list that we've sort of formulated for ourselves to add in optional pseudopotentials for some things if we can. Where pseudopotentials certainly exist, and that's relevant for catalysis, is as embedding pseudopotentials, so electron-free pseudopotentials in the context of embedded cluster methods, for example. So ChemShell from Cardiff that was mentioned on one of the slides, one of these methods, and that's definitely something where they've been used for a long time in FHI-aims. We do have a frozen core approach implemented in FHI-aims that also reduces the computational effort, especially for large systems, if you're interested in just working with a set of valence semi-core electrons, and that's also documented.
So maybe I can add actually, because I mean Ray already said it could be that the question was a little bit misspelled, because on the fly sounds a little bit like machine learned potentials. So what we have already, but not public, but it will be public in a month or so, is on the fly machine learned potentials for geometry optimization, and we are working on it. So probably there will be a webinar in August where we will have all the machine learning aspects which Ray has mentioned, including really machine learned potentials. And I should also say, maybe later Konstantin will say that anyhow, we will have an in-person meeting in November in Shanghai, where we also have a full session on artificial intelligence, including CISO and machine learned potentials and deep H. So that exists already, but it's not public. So there is a beta version which you can get, but otherwise, if you wait for 2 months, and it will be really public as part of the GIMS, of the graphical user interface.
Thanks a lot.
Sounds very exciting.
Yeah. There's also one question from Hashitl to Ray. What criteria did you use to select the orientation of the nanoparticle to be absorbed on a substrate?
Okay, yeah, that's a very good question. So, yeah, actually, I skipped at this part. So, actually, I picked up the most planar, how to say, the side of the metal cluster. And actually, that is the reason why, I know the, metal cluster is interaction between the metal cluster and the support material is stabilized by interaction with oxygen atom. Then I'd like to, how to say, maximizing this interaction with metal nanocluster and the support material. And then I picked up the most planar and the most large facet of the orientation of the cluster when it interacts with the silica slab. And then I picked up this most planar site. I hope this is the answer for this.
Thanks a lot. There is one more question from anonymous attendee. How do you consider the magnetic behavior before making a slab?
Okay, good question. So actually for silica, there's a no magnetic, no complicated magnetic structure, I believe. So this is a singlet state. But for cobalt cluster, yeah, actually I picked up the, this cobalt cluster structure from the previous report. And actually that previous report also investigated those two papers, investigated the magnetic structure of the cobalt cluster. And then actually even for, the bulk cobalt, the ground state is a ferromagnetic state. Then I put the, triplet state of the each cobalt atom as the initial spin state for geometry optimization. And then after the SCF calculation and geometry optimization, of course, the optimized electron structure is slightly deviate from the original triplet state, but keep the ferromagnetic state. And it is actually stable than the singlet state. And another point is, as I mentioned, actually in my another study, this is a gold nanocluster is supported on the manganese oxide. For manganese oxide, we need to think about the spin structure. In this case, in experiments, the anti-ferromagnetic structure is reported as the most stable one, and then I put the anti-ferromagnetic structure as the initial spin state for geometry optimization or SCF, and then actually after the SCF we can get the stable anti-ferromagnetic structure. Then you are right, actually before performing the calculation we need to know or investigate the most stable spin or magnetic structure of each material. Yes.
Thanks a lot. Hope this answers the question. Yeah, there is one more question from Oscar van Vuren. Have you considered the possibility of cationic defect species from the silica migrating into the cobalt nanoparticle? Is this something that your experimental collaborators could probe?
Actually, that is also a very nice question. So, yeah, that is unknown. Even now, it is very unknown part for me. So, actually, my experimental collaborator mentioned that for particularly for titanium case, they investigate this kind of, distribution of the titanium region at the silica support. And then they found that, for example, for zirconium or aluminum, those species are, randomly disparted at the silica. That means, atomically dispersion. But for titanium, they found that, of course, there's some kind of atomic site of the titanium, but they also found the kind of island structure of the titanium oxide at the interface. That means as you know, the titanium oxide probably making some kind of cationic or charged defect of the oxygen. Then that would also contribute to the high catalytic activity, I think. But as I mentioned, it is unknown things for me because this is actually experimental information, but the very complicated thing, then we need to carefully investigate this. And actually in this study, we would like to make some data for AI, and then this kind of special data for titanium is not so good for AI because those kind of data or information are lacked for zirconium or other metals. Then I have not carefully focused on this part, but in particular at the operant situation, probably this kind of oxygen defect formation and, for example, stabilizing the metoxic species at the defect would be possibly happen. But that is, we need more how to carefully modeling this, and also experimental, based on the experimental metal ratio at the surface, we need to put at least 10 titanium atoms on the surface. But in this model, I only put 1 titanium atoms, as I mentioned in my talk. Then this is a approximated model for the catalytic system. But if you are interested in this kind of oxygen defect, we need to make a more realistic model for catalysis.
Thanks a lot. There is a next question from Zhaoqing Liu from CoShare, and the same question was asked by James Misaka. How do you perform basis set superposition error in FHI-aims for catalysis, particularly for absorption energy?
Yeah, good question. Actually, for this calculation, I haven't adapted any BSSE correction. But in my understanding, recently it was implemented in the FHIs, right?
I can comment.
Yes.
So I think this is a frequent question from the quantum chemistry community, but it's also actually one of the strengths of the NAO basis sets for DFT, that we don't need a BSSE correction in practice. So this is already addressed in the first FHI-aims paper in 2009, and that experience has not changed. So the DFT BSSE errors that are reported elsewhere, I think they often arise near the nucleus, and our NAO basis functions near the nucleus actually are very good and very precise. So the BSSE we have is very small, and so we carried out tests initially, and those tests indicate that our basis set error is not even close to primarily BSSE. In fact, if you want to increase the basis set, you may improve other things of the density, but the BSSE is not the biggest problem. And so we don't need a BSSE correction for density functional theory calculations typically. And for correlated methods, this is different because you have a sum over unoccupied states, and there we can do a BSSE correction. And I think that's what Ray is also referring to, that there's a recent discussion about BSSE correction and how to do that for periodic systems in the right way for a random phase approximation. But for the calculations here, it actually isn't a strong necessity. So they work without all over FHI-aims.
Thank you, Volker.
Thanks, Volker. I hope this answered the question. There are several more questions. So one question is from anonymous attendee. What are your thoughts on using Bade charge instead of threshold charge?
Okay, so that is also a good question. So actually, first of all, when I performing this calculation with FHI-aims, there's no implementation for generating the appropriate charge density for performing the beta charge analysis. Then I picked up the Hirschfeld charge analysis implemented in FHI-aims. But after that, that formation generating the electric density for beta charge analysis was nicely implemented in the FHI-aims, then now we can perform the beta charge analysis with FHI-aims. But important point is there's a no golden standard for charge analysis, because that is very, how to say, artificial analysis. Then because we have to how to say, decide where is the electron located, but in real, electron is moving around. Then my opinion is, okay, even with hash rate analysis or beta charge analysis, we need to be checked with those results with different aspects. For example, this charge density difference. Charge density difference is just how to say, raw kind of raw data of the electron structure, and then this is just a difference between the interacted system and the isolated system. And then here, as you can see here, yellow region is the electron accumulation region, and the blue area represents the electron depression region. That means here the charge transfer from support material to cluster is nicely represented. And also in this system, I performed also a hash rate charge analysis, and the hash rate charge analysis also shows the charge accumulation at the cobalt cluster. Gold cluster. That means that those two results are in good agreement with each other. That means the charge density, population analysis is very nicely worked for this system. Probably kind of similar result would be obtained even with beta or NPA or Barrican charge analysis. But the important point is we need, in my opinion, we need to check the electric structure with different aspects, like those charge density difference or population analysis. This is my opinion.
It's not great. And there are two more questions by Masood. How do you find the morphology and the size of the supporting cluster?
Okay, thank you. And I actually, sorry, I completely forgot about the mentioning about the thank for the previous study. And actually, in those two studies, they are investigated the stable structure of each size of the cobalt cluster by using global optimization method. And then probably in this reference number 1, they investigated the several sizes of the cobalt cluster, and then actually I picked up the cobalt 20 cluster because this is a how to say, I would say for me at that time upper limit for performing the DFT calculation for simulating the catalysis for my environment, and then I picked up this one. But then I haven't myself haven't performed the any global optimization, but thanks for these previous studies, I can pick up the stable cobalt cluster in the gas phase. Of course, I don't know the stable structure of the interact with the silicon and cobalt, but we needed to pick up this kind of stable cluster at the gas phase as the initial structure for geometry optimization.
Thank you. One more question from anonymous attendee. Have you taken the van der Waals forces into account in your calculations? So these forces can significantly influence the properties of molecules, especially in systems where intermolecular interactions are important. It's essentially to include them for accurate results.
Yeah, right. So actually, in this calculation, I just use the simple RPBE without any van der Waals correction. But before performing this calculation, I have checked the accuracy of RPBE and RPBE with van der Waals correction. For this, I adopted Takechenko-Sheffler type van der Waals correction. And actually, I investigated the CO, absorption energy of the carbon monoxide on the cobalt surface, because there is some experimental report for the adsorption energy and the vibrational frequency of the CO on the surface. And then I realized that, as other people mentioned, van der Waals interaction is very nicely for represent the adsorption of the how to say, physics of the molecule on the metal surface. But if we directly use not without correction, the van der Waals correction for chemists of the structure, actually adsorption energy of the small molecule is largely overestimated. And even actually, indeed, for the carbon monoxide adsorption of the cobalt surface, adsorption energy of the DFT are largely how to say, deviated from the experimental result. If I put the van der Waals correction, then I decided to not use the van der Waals correction for this calculation. And of course, I also investigated the lattice constant of the bulk cobalt with RPB, and then those are also well represented. And vibration frequencies of the CO molecule on the cobalt surface is also nicely represented by bare RPB. Then I decided not to use the van der Waals correction for this.
Okay.
Maybe I can add a little bit to that. So what we find in general is that the Tkachenko-Scheffler, which was the very first development, right, is somewhat overestimating van der Waals corrections. And if you come to short distances, PBE, in fact, has some van der Waals included, obviously, already. So in general, if you want to include van der Waals, I think one should also go beyond Tkachenko-Scheffler, but one should really go to the many-body dispersion to have a more realistic thing. But again, for short distances, if you really look at chemisorption, that is not so important for these systems. For other systems, if you would have layered compound or something, of course, then you should include many-body dispersion. But the Tkachenko-Scheffler is giving you an idea, but I would say you should really go to the next generation.
Okay, thank you very much.
Thanks, Matthias. Unfortunately, we are short on time, so let's do one last question, I guess. Dr. Sutagema asks, are the energies in your results compared with experimental results? If yes, how are the single point DFT energies corrected for better comparison with experimental data?
Actually, that's a very difficult question, I would say. Ideally, we should compare our result with experimental data. And for some systems, we can do that. But for heterogeneous catalysis, it is very difficult to get a reliable experimental result that can be compared with DFT data. Even for adsorption energies, it is very difficult to get them. And actually, I have asked our collaborator to get some kind of data, but it's a bit difficult. But I would say, actually, as I mentioned in the previous Q&A session, I found some kind of experimental data for carbon monoxide adsorption of the cobalt surface. This is the, surface science topics. But it can be compared with DFT. And then, as I mentioned, RPB functional is qualitatively represents the experimental result. Then, RPB is not so bad selection for this simulation, I would say.
Okay. Thank you, Ray, again.
Thank you very much.
As Andre said, we're a bit low on time now. I think that also handles most of the questions. Maybe last one we can just answer in chat. Maybe that's easier. So I want to thank Ray, of course, again for giving the talk. I want to thank our panelists for answering questions and helping. And of course, all the attendees who are still here. And I think we had a very lively Q&A session. So I want to thank everyone for contributing. And then lastly, I just wanted to point out again the plan for tomorrow. So if you're interested in trying out the code in FHI-aims, maybe you want to see it in action, see it for yourself. We have the hands-on discussion sessions in the morning Europe time, so 9 a.m. CEST, as well as 3:30 p.m. CEST, where we will run through some of the examples that Ray has shown. So we'll see, for example, results for the cobalt cluster, how can you actually model the cobalt cluster, and as well as, for example, here on the right side, the cobalt cluster adsorbed on the silica support. So if you're interested, please come. You can, of course, ask more questions tomorrow. And yeah, I hope to see a lot of you there. You still have time to sign up. So if you go back to the Indico page, you can still register also there to be part of the tutorial sessions. But with this, I would then close today's webinar. Again, thank you, Ray. Thank you all the panelists, as well as everyone who was here. I think it was a very nice webinar. As Matthias mentioned, there is a planned workshop happening in November. We will most likely announce it either at the end of this week or early next week. So keep an eye out. We'll try and send it around on our social channels, different mailing lists like FHI-aims and so on, as well as our website. So if that's of interest to you, please have a look, and maybe we can see each other also in person in Shanghai in November. Otherwise, always remember that we also post our upcoming webinars on our channels. We have new ones planned, which we'll announce shortly. So please keep an eye out for more webinars of this sort. And again, I hope every one of you enjoyed being here. And one last time, thank you to Ray and everyone here. And with this, I would close the session. So thank you, everyone. See you all next time. Bye-bye.
Yeah, thank you very much.